Hi, I'm Julian from CMU, and here I'm going to talk about our works in physics-informed machine learning with misspecified priors, and the data is based on the turning operations in the layer machine. So first, we want to state what PIN is. PIN is basically a neural network that is trained by some physical guidelines, and typically it's guided by differential equations. Here we use LU equals to F to represent the differential equation and BU equals to G to state the boundary or initial conditions. And what we want is the equation solution U. The vanilla PIN is trained by minimizing the MSE error of the differential equation values and the boundary condition or initial condition errors. And many recent works explore the possibility of using a data regularized term to give better performance, where they assume that they can access to some measurement data of exact solution. However, here we argue two realistic problems. The first one is that most current works assume that their measurement data are uniformly sampled, but in many cases it is impossible. For example, getting measurement data under high velocity or high temperature is extremely difficult, or some machines cannot run for a long time, so the data from later time domain is not accessible. Then the even worst case is that sometimes we cannot get any measurement. And under this case, PIN always fails to learn the exact solution for some equations, typically homogeneous equations. And our goal here is to address the solutions for these two cases. First, we want to show the case of learning with limited noise data and misspecification. The misspecification means that there could be some difference between exact equation coefficients and that we used for learning. So here, we show that even with misspecification, PIN can still converge to the true solution if with some data regularizations. This is verified by the left figure, where the orange curve is the data, the blue curve is the expert, the pure data model is given by the green curve, which causes heavy overfitting, but the P model actually gives a smoother and more reasonable result. Then, to solve the problem of limited data mentioned in previous, we proposed a method of PIN plus convolutional LSTM or DNN, where we first learn a PIN estimation and then use the estimation to learn a LSTM or DNN model for long-term prediction. The result is shown in the red figure, where we assume only data from first half time domain is available, and our method gives a good prediction in the long term, even at a domain without training data. Second, we want to figure out how to overcome the failure cases where there is no data regularization. Previous works have shown that PIN tends to learn some smoother or trivial solutions for some problems, especially when the solution's frequency is high. Here we argue that this is because the boundary condition or the initial condition can only be a constraint to where zeta is close enough to them. For the domain, zeta is far away from the boundary or initial conditions. PIN can actually learn any arbitrary solutions that fits the equation, and they are typically constant solutions for homogeneous equations. That is, PIN is trying to learn some combined solutions, which is analytically wrong but numerically possible. To overcome this, we modify the previous seek-to-seek training method, where it trains the neural network piecewisely, and the last prediction from previous neural networks serve as the initial or the boundary conditions for the next neural network. We argue that this method can actually lead to very slow convergence for later networks. So we do two things. The first is to reduce the frequency during training and do reconstructions later. And the second is to hard-code the boundary and initial conditions. And our result shows a faster convergence and better performance compared to the original seek-to-seek training. Overall, we can draw a conclusion that our work shows that PIN can learn a reasonable estimation even with noise data and a misspecified expert. We also proposed a method of PIN plus convolutional LSTM or DNN that can help learn the estimation for long-term prediction, even as the domain without data. And we also proposed a modified seek-to-seek training that leads to faster convergence and shows better results than the original techniques.
Hi everyone, my name is Ranjan and I'm a PhD candidate at MIT. And today I want to talk to you about predicting the system response of arbitrary nonlinear systems using surrogate models. Now the question is, why do you want to do that? So firstly, you could design controllers using this type of surrogate model. You would be able to predict the system response in with respect to some sort of control input and use this as feedback to design the controller. And another reason is you could accelerate the simulation of large systems, especially if they're component based and especially if they're causally connected. By which I mean the output from one particular component goes as input to the other component. In which case you'd be able to get the system response, which then goes into another component. So you'd be able to replace one of these components with a surrogate and thereby accelerate the simulation. All right, now, how exactly are we going to do that? So one particular option is to take, let's say, the system, a list of the system parameters, I'm going to call them P, and you could, what you could do is you could then parameterize the input that goes into the system by another set of another set of parameters, which I will call the forcing parameters, which say P prime. And then what you can do is you can then train a parametric surrogate, which takes in the concatenated vector P and P prime and gives you the prediction for the output time series. Now, the trouble with this sort of formulation is that it treats P and P prime exactly the same way, which you may not want because P prime has a different sort of effect on the dynamics as opposed to P, which are the system parameters. All right, now, what are we going to do about that? So to discuss it, I need to introduce this surrogate methodology called the continuous time echo state network, which is especially good at learning the multi-scale dynamics. So it's multi-scale in time, which are present in a lot of engineering systems. Think of buildings with heat dynamics that happen over a slow scale and little controllers within the buildings that happen at a really fast scale. Or little changes, or room dynamics that happen at a very fast scale. All right, now that we have a surrogate that is good at that, how do we then predict, let's say, the change of a building with respect to some control input? So first, let me introduce the continuous time echo state network, which consists of these two equations over here. The first equation is called a reservoir, which is why it's given by R, and this reservoir equation is designed. So it is a system that is cheap to simulate, and it will capture properties of the original system, except at a much faster sort of rate. So, for example, if there is a discontinuity at a particular point in time, and you knew this in a priori, you would put that in this reservoir equation. And then what you do is you then go to the expensive system, and then you learn a projection from this cheap system to the expensive system. And so the surrogate in and of itself would be a combination of the reservoir and the projection. So a simple parametric surrogate, which just takes in a set of system parameters and spits out the time series, would do something like this. But if you wanted to have a forcing function, a forcing term in here, you would need to modify the reservoir equation to take this forcing term. And now the reservoir is capable of giving you system responses. And so what you do is then you learn a projection, this projection from all the reservoir responses to a particular set of forcing functions to the system responses, with respect to a particular set of forcing functions. And then you would do this at every system, at a bunch of system parameters, and then you would learn an interpolating function that then predicts this projection. And then you would then propagate the force through your reservoir, and then you would get the system, and then you would use a matrix vector product to get the system. All of this has been explained in the paper. The point is this sort of formulation is meant to treat certain parameters different from other parameters, which I think is the key powerful idea. And so we've demonstrated this working on a couple of examples here. One's the inverter, one's an inverter, one's a digital to analog converter. If you can see, this is a picture of the reservoir response with respect to the inverter, and you see that it is able to capture these transition points that are very typical to the system, and that's what a reservoir is meant to do. And and of course, we are able to capture this with a low level of accuracy. And as for the digital to analog converter, which is a much, much larger system, we're able to demonstrate a 274x speedup. I hope this little blurb has piqued your interest in finding out more about our paper and our poster. So I'll be around the conference. Feel free to ask me any questions, and if you'd like to collaborate, we would absolutely love that. Thank you.
Hi everyone, my name is Søren Taverniers, and today I would like to discuss about our work on accelerating part scale simulation in liquid metal jetting through the use of operator learning. This work was done at PARC, a Xerox company. The key challenge we want to address is part scale quality prediction for a liquid metal jet additive manufacturing. This typically requires high fidelity simulations of the governing equations. However, these simulations may become very expensive when building full parts that may contain up to millions of droplets. As a result, reduced order or surrogate models were developed that are computationally more tractable. However, they may at the same time lack accuracy and robustness, and also may not generalize well beyond the training data. As an example of such prior approaches, we highlight the work by Korneev et al., who first built a high-fidelity open-foam model for single droplet coalescence events, as pictured here, which are applied along a prescribed toolpath in a moving subdomain. The authors then replaced this open-foam model by a k-nearest neighbor search within the open-foam data. And while they achieved a 20,000 times speedup compared to open-foam, because it was a search algorithm, it extrapolated poorly out of training. Therefore, the authors came up with a new approach involving a fully connected neural network to approximate the mapping between the initial and final states, which were represented by the combined liquid and solid phase fractions. And what they found was that while this seemed like a good idea, the network size required for accurate prediction beyond just a few sequentially deposited droplets became prohibitively large. What we wanted to do then is to go further on these previous approaches and use the idea of operator learning to improve this mapping between initial and final states. And rather than using a fully connected network to approximate this mapping directly, instead we used the recently developed Fourier neural operator, or FNO, to learn the kernel integral operator related to the PDE's Green's function. This method is schematically represented here, where we have a series of identical so-called Fourier layers, which each consist of several parts, including a forward and inverse Fourier transform along with low-pass filter, together with a residual connection and a nonlinear activation. We then trained and tested the FNO model using open-foam data from part simulations, where we use different part shapes for the training and test data to make them independent of each other. And by tweaking the network complexity, we then arrived at the following test error distribution visualized here that had a peak or mode just above 10%. We then used the trained model to first of all predict single droplet lines, where we have lines of droplets that are deposited with various spacings between the droplets. And here on the right, we show for 3 different spacings the comparison between the FNO predicted isosurfaces on the left and their corresponding open-foam ground truth on the right. And we see that the predictions are fairly accurate. In addition, we also found that the prediction with FNO was 1 order of magnitude faster than with KNN. And as a result, FNO could enable real-time prediction of part shapes for realistic deposition frequencies, although further reduction in overhead is needed. Next, we did a qualitative assessment for stacked droplet lines and found that diversifying the training set yielded a more accurate prediction of the involved features. In the future, we plan to do a full quantitative error analysis for full part shapes to see if FNO can handle full parts. And we also want to add physics-based regularization to the loss function so that FNO can be compatible with the governing conservation laws. We also want to compare FNO with other operator learning approaches and extend the analysis to more complex material properties. Thank you for your attention.